Hi students, in this video you will learn about the concept of Hess's law. Hess's law was proposed by Hess, a chemist and a doctor. Hess's law states that when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in the series of steps. In other words, the enthalpy change of a reaction is independent of the route taken. The statement is illustrated in this diagram. The triangle shown is called energy cycle. When A reacts with B to form C, the enthalpy change for this reaction is delta H1. Then we have delta H2 for the reaction of A and B to form D. For the formation of C from D, the enthalpy change is delta H3. For route 1, the sum of heat change is delta H1. For route 2, the sum of heat changes is delta H2 plus delta H3. According to Hess's law, delta H1 is equals to delta H2 plus delta H3. Let's refer to the following energy cycle. In this energy cycle, you can see the conversion of X to Y involve multiple routes or steps. For route 1, the enthalpy change is delta H1. For route 2, the sum of enthalpy change is delta H2 plus delta H3. And for route 3, the sum of heat changes is delta H4 plus delta H5 plus delta H6. According to Hess's law, these are the relationships. The enthalpy change of a reaction cannot always be directly measured. Hess's law allows the enthalpy change for a reaction to be calculated even when it cannot be measured directly. Alright students, we will continue the calculation involved Hess's law in the next video. Stay tuned. Thank you. Hi students, let's continue the lesson with Hess's law calculations. At the end of this video, you should be able to solve Hess's law problems using algebraic method. This is the question. Calculate the standard enthalpy of formation of methane, CH4, by using the following equations. In this question, you were provided with the thermochemical equation whose enthalpy is to be calculated. You also were given thermochemical equations for reactions whose enthalpies are known, labeled with delta H1, delta H2, and delta H3. Now, let's learn how to solve these problems by using algebraic method. Step 1. Identify and write the target equation. The thermochemical equation for reaction whose enthalpy is to be calculated, which is given in the question, is the target equation. Step 2. Write all thermochemical equations for reactions whose enthalpies are known. These equations were provided in the question. Step 3. Rearrange all the thermochemical equations from step 2 to correspond with the target equation, which is from step 1. According to the target equation, 1 mole of carbon appears at the left side of the equation, and carbon appears as reactant. Carbon only appears once, which is in equation 1. But since the coefficient of carbon in the target equation is 1, so equation 1 is remains. For hydrogen gas, the coefficient in the target equation is 2. And hydrogen gas appears as reactant. From the thermochemical equations given, you will notice that hydrogen appears once in equation 2. But since the coefficient of hydrogen gas in the target equation is 2, so equation 2 is multiplied by 2. The whole equation 2 is multiplied by 2, including the delta H2. So now, the thermochemical equation becomes 2 mole of hydrogen gas reacts with 1 mole of oxygen gas, produces 2 mole of water liquid, and the value of delta H2 becomes negative 571.2 kilojoule. Since 1 mole of methane gas appears at the right side of the target equation, equation 3 must be reversed. This will change the sign of delta H3. Thus, the thermochemical equation 3 becomes 1 mole of carbon dioxide gas reacts with 2 mole of water liquid, produces 1 mole of methane gas and 2 mole of oxygen gas. And the value of delta H3 becomes positive 753.0 kilojoule. Step 4. Combine the rearranged equations. Add all the enthalpies from step 3 to determine the required delta H. To obtain the target equation, the 3 equations are added to give, after cancelling, the enthalpy change for the reaction. So, you can see here, 2 mole of oxygen gas are cancelled out. 1 mole of carbon dioxide gas also cancelled out. And 2 mole of water liquid are cancelled out, leaving 1 mole of carbon solid, 2 mole of hydrogen gas, and 1 mole of methane gas. The remaining elements and compounds are same as stated in the target equation. So, how to calculate the required enthalpy? By applying the Hess's law, where enthalpy of the reaction is equals to delta H1 plus delta H2 plus delta H3. Substitute all the values of the enthalpy and you will get the standard enthalpy of formation of methane is negative 211.7 kilojoule per mole. Alright class, I hope this video will help you to solve the Hess's law problems. Thank you. Hi students, let's continue our lesson with Hess's law calculations. At the end of this video, you should be able to solve Hess's law problems using energy cycle method. This is the question. Calculate the standard enthalpy of formation of methane, CH4, by using energy cycle method. How we are going to use these three thermochemical equations to construct an energy cycle by calculate the enthalpy of the reaction. Okay, let's start. First, write the target equation. So we have 1 mole of carbon solid reacts with 2 mole of hydrogen gas and forms 1 mole of methane gas. The enthalpy change of the reaction is unknown. Next, how we are going to use thermochemical equation number 1, number 2 and number 3 to link with the target equation. In the energy cycle method, the equation for which the enthalpy change is to be calculated are connected to other equations by a set of arrows with the corresponding values of enthalpy changes written on the arrows. Alright. If you refer to the thermochemical equation number 1, we have 1 mole of carbon solid appears as a reactant. In the target equation, 1 mole of carbon solid appears as a reactant. So now, let's link this equation together. 1 mole of carbon solid reacts with 1 mole of oxygen gas, produces 1 mole of carbon dioxide gas. The enthalpy change for this reaction is delta H1, which equals to negative 393.5 kilojoule. Settle with thermochemical equation 1. In the thermochemical equation number 2, we have 1 mole of hydrogen gas appears as a reactant. But in the target equation, we have 2 moles of hydrogen gas appears as a reactant. To link the thermochemical equation 2 with the target equation, equation 2 must be multiplied by 2. So now, let's link the equation. 1 mole of hydrogen gas become 2 mole of hydrogen gas, reacts with 1 mole of oxygen gas, produces 2 mole of water liquid. The enthalpy change for this reaction is equals to negative 285.6 kilojoule times 2, which is equals to negative 571.2 kilojoule. So now settle with equation 2. In the target equation, we have 1 mole of methane gas. In equation 3, we have 1 mole of methane gas appears as a reactant. And now we are going to link 1 mole of carbon dioxide, 2 mole of water liquid to form methane. So we are going to link this equation 3 with methane. Equation number 3 must be reversed. So the equation becomes 1 mole of carbon dioxide gas reacts with 2 mole of water liquid and 1 mole of methane gas produces 1 mole of methane gas and 2 mole of oxygen gas. So now we can link equation number 3 with methane. So now we can link 1 mole of carbon dioxide gas with 2 mole of water liquid, which produce 1 mole of methane gas and 2 mole of oxygen gas. The enthalpy change of this reaction is delta H3, which is positive 753.0 kilojoule. From the energy cycle, we can see there are 2 routes to form methane. The first route involves 1 step, where 1 mole of carbon reacts with 2 mole of hydrogen gas. So this is route 1. So for route 1, the enthalpy changes is enthalpy of reaction. But formation of methane may involve multiple steps. For route 2, it involves 3 steps. So this is the first step, second step, and this is the third step. So the relationship between enthalpy of the reaction with route 2 is enthalpy of the reaction is the sum of delta H1 plus delta H2 plus delta H3. By applying Hess's law, we are going to apply the Hess's law to solve the problems. So, enthalpy of the reaction, substitute all the values of enthalpies, equals to negative 393.5 kilojoule plus negative 571.2 kilojoule plus positive 753.0 kilojoule. The enthalpy of the reaction is negative 211.7 kilojoule. But the final answer must be written as negative 211.7 kilojoule per mole. Alright students, I hope this video really helps you. Thank you. Hi students, let's continue our lesson with calculating enthalpy of reaction from the standard enthalpy of formation. Standard enthalpy of formation is defined as the heat change when 1 mole of a compound is formed from its elements in their most stable state at standard conditions. Standard enthalpy of formations are very useful because they can be used to calculate the enthalpy of reaction. The relationship is given below. Enthalpy of reaction is equal to the sum of the standard enthalpy of formation of products minus the sum of the standard enthalpy of formation of reactants. Let's look at this example. Calculate the enthalpy of reaction for the following reaction. Given to you in the question a balanced chemical equation and the standard enthalpy of formation values for propane gas, carbon dioxide gas, and liquid water. You can see the value of standard enthalpy of formation of oxygen gas is not listed. Since the elements are formed from their respective atoms or elements, the standard enthalpy of formation of any element in its most stable state form is 0. Thus, the value of standard enthalpy of formation of oxygen gas, which is in its most stable state, is 0 kJ per mole. Now, how to solve this question? We have to use the balanced chemical equation and all these informations given. By using this relationship, first, we are looking for the sum of the standard enthalpy of formation of the products. We have carbon dioxide gas and water liquid as the products. In the balanced equation, the coefficient for carbon dioxide gas is 3. So, the values of the standard enthalpy of carbon dioxide gas is multiplied by 3. Since the coefficient for the liquid water in the balanced chemical equation is 4, therefore, the values of standard enthalpy of formation of liquid water is multiplied by 4. This is the sum of the standard enthalpy of the products. Next, subtract with the sum of the standard enthalpy of formation for the reactants. We have 1 mole of propane gas in the balanced chemical equation and 5 mole of oxygen gas. Thus, the value of standard enthalpy of formation of propane gas is multiplied by 1. Plus with the standard enthalpy of formation of oxygen gas. Substitute all the values. Be very careful with the sign of enthalpies when solving this question. The answer for this question is negative 2,219.95 kilojoule. Alright students, we will continue in the next video. Stay tuned. Hi students, let's continue our lesson with dissolution process of ionic solids. Dissolution is the process by which solid forms a solution in a solvent. Most ionic compounds are soluble and dissolve in water to form solutions. Dissolving ionic solid in water produces measurable heat change. Heat change during dissolution of solid ionic compound is either exothermic or endothermic. Enthalpy of solution is defined as heat change when 1 mole of solid ionic compound dissolves in solvent, which is water, to form an infinite dilute solution. For example, when 1 mole of solid sodium chloride dissolves, 4 kJ energy must be absorbed for the process to occur. What happens when solid sodium chloride dissolves in water? In the solid sodium chloride, the sodium ions and chloride ions are held together by strong electrostatic forces. But when a small crystal of sodium chloride dissolves in water, the crystal lattice breaks into sodium ion and chloride ions. The separated sodium ions and chloride ions are stabilized in solution by interaction with water molecules. These ions is said to be hydrated. The solution process takes place in 2 steps. First, breaking down of the crystal lattice into isolated gaseous ions. Sodium ions and chloride ions in the solid crystal are separated from each other and converted to gaseous state. Energy must be absorbed for this process to occur. Energy required to completely separate 1 mole of a solid ionic compounds into gaseous ions is called lattice energy. In this example, the lattice energy of sodium chloride is 788 kJ per mole. In other words, 788 kJ of energy must be absorbed to break 1 mole of solid sodium chloride into 1 mole of sodium gaseous ions and 1 mole of chloride gaseous ions. Next, the hydration of separated gaseous ions by water molecules. Gaseous sodium ions and chloride ions enter the water. Each ion will be surrounded by water molecules and become hydrated. In this example, when 1 mole of sodium gaseous ion and 1 mole of chloride gaseous ions hydrated, 784 kJ energy or heat was released. The energy cycle diagram of the process of dissolution of sodium chloride is as follows. Enthalpy of hydration is defined as heat released when 1 mole of gaseous ion is hydrated in aqueous solution. By applying Hess's law, the enthalpy of solution is the sum of lattice energy of sodium chloride and enthalpy of hydration of chloride ions and sodium ion. In this example, the enthalpy of solution of sodium chloride is positive 4 kJ per mole. Thus, When 1 mole of solid sodium chloride dissolves in water, 4 kilojoule of heat or energy will be absorbed from surroundings. Alright students, we will continue the next subtopic in the next video. Thank you.